Bonjour and welcome to these office hours. Today I am at the Louvre, one of the largest museums in the world, holding quite a few famous pieces such as the Mona Lisa by Leonardo da Vinci. But beside the famous pieces, there are beautiful other pieces. For instance, there is one of my favorites, the Egyptian section of the Louvre, and this Egyptian section holds more than 50,000 pieces. Some of them are absolutely magnificent, and I strongly suggest you come visit the Louvre, pay a visit to this beautiful museum if you come to Paris, either as a tourist or as a student of École Centrale Paris. Today I would like to talk about Sobolev spaces, questions that were asked with respect to week 7, and also give you the answer to the joke we talked about last week. That joke, remember, was about the Hilbert Hotel. Now, if you remember the joke last week, we talked about the Hilbert Hotel, which is a hotel with an infinite, countable number of rooms. And the point was that the hotel was full, no vacancy, and a guest would show up, a new guest would show up, and Hilbert says, well, just move people who are in room N to room N plus 1. And that frees up a room so the new guest can be accommodated. Now the question we asked was, what would you do if an infinite, countable number of guests would show up? And the answer is, well, you just ask the guest at room N to go to room 2N, which frees up an infinite, countable number of rooms. These rooms are numbered with even numbers, and that will allow you to get this countable number of guests in the hotel. Now, probably some of you are thinking, well, this punchline is not that funny. Well, it is actually quite interesting, because what it says is that you can somehow fit two n's, two sets of integers, in the set of integer. Of course, said like this, it kind of makes no sense, but what it really means is that you can have a bijection between the set of integers, natural integers, and the set of integers that can be positive or negative. And even though that is counterintuitive, it is quite interesting to see this in the context of talking about countable numbers. Alright, now this joke being told, let's actually move to the material of week 7. And the first thing I would like to say is why we're doing all this. Why are we talking about Sobolev spaces? Why did we talk about LP spaces last week to begin with? Well, this is because it is the good setting to deal with modeling, partial differential equations, and somehow mathematical physics. And I'm going to give you an example of why we would be sad if we had to deal with spaces such as C or C1, the set of continuous functions, or the set of continuous functions that can be differentiated once and for which the derivative is continuous. Let me give you an example immediately. If you look at the set of continuous functions on set 0, 1, and you actually choose the norm, which is the integral between 0 and 1 of the absolute value of the function, and that is a norm. And it's actually a norm that arises pretty often in physics. Actually, if you look at the integral between 0 and 1 of the absolute value of f squared, then this is actually a norm that comes up quite often in physics because it will actually talk about the energy of a system, often. So what I'm saying is that this norm is pretty useful, and this set of continuous function is pretty natural, I would say. Now, if you look at it, there is a major flaw in this vector space. The flaw is that the vector space is not complete. It is not a Banach space. It is a norm space, but it is not a Banach space. It is not complete. And to show you that it is not complete, I would like to show you this sequence of functions. You see, the functions that are equal to 0 from 0 to 1/2 minus 1 over n, and that are equal to 1 from 1/2 plus 1 over n to 1. And in between, I just put a straight line, so it's easy actually to compute this the equation of this function. But what happens is that obviously this function is in C 0, 1. I mean, this function is continuous. Now, if you look at what happens when n goes to plus infinity, you can see that this will converge to a function which is 0 between 0 and 1/2, and 1 between 1/2 and 1, which is not continuous. So what I'm saying is that this function, this sequence of function, which by the way is a Cauchy sequence, very obviously, will converge, but will not converge in C01. So C01 is not a Banach space. However, if I go to L1 with this same norm, then in L1 things are going to work out. L1 is a Banach space. Remember, we proved it. We proved that LP spaces are Banach spaces. So what I'm saying is that if you want to deal with this norm, and very often you have this norm, or the integral between 0 and 1 of f squared, and very often you have this norm, then C is not the good space to work with. While L1 or L2, if you take the norm square, I mean the integral of f squared, would be a good setting for it. And the same thing goes if you have derivatives and you want to deal with a set of functions that are in C1, right? I mean the functions that are continuous, that can be differentiated, and for which the derivative is continuous. That is C1, in this case C1 of 0, 1. You could want to deal with the norm of, well, for instance, the integral between 0 and 1 of the norm of the function plus the norm of the derivative. And you would have a problem. C1 with this function, this norm would not be a Banach space. So that is a problem. And what I'm saying is that this is not the good setting to work with this norm. The good setting in this case would be what we introduced this week. The good setting would be a Sobolev space. So you see, completeness is useful. It will allow us to use the Lax-Milgram, for instance. I mean, this is a good setting because you can use the Lax-Milgram theorem. Also, when we're talking about completeness, we're talking about the density somehow. We're talking about the way to approximate functions by other functions. And when you deal with algorithms and with converging sequences, it is very useful to be in a situation where you can approximate your function that you're looking for by a sequence of functions that will converge to the functions you're looking for. So this is why it is so important to deal with this setting, these Sobolev spaces. So again, what we have is we have WMP spaces, which are Sobolev spaces, and when m is equal to 2, what we happen to have is a Hilbert space, which means that you have a scalar product, and these will be called HP spaces. And so if you go back to the lectures, you will see the definitions for these spaces, and this is why we are using Sobolev spaces. It is because it is the good settings for partial differential equations and for modeling physics. We will see that we will model a membrane, and the model of the membrane will give us a PDE, a partial differential equation, and what we're going to do is show that we have a solution, and a unique solution, thanks to Lax-Milgram, and it is very useful then to have the proper spaces, and you will see that we will need Hilbert spaces, and we'll need, Sobolev spaces. And then we'll actually go all the way to the numerical simulation. Another thing that I wanted to say is about Sobolev embeddings. And the question about Sobolev embeddings is, well, first of all, if I look at a Sobolev space WMP, how smooth are the functions that are in this space? Are the functions continuous, for instance? And the Sobolev embeddings answer this question. What we're saying is that if m times p is greater than dimension of the space, then the answer is yes. Also, we have embeddings such as, can I say something about the norm LP of a function based on the norm LP, or actually LQ, of a derivative, and vice versa. From the norm LQ of the derivative, can I say something about the norm LP of the function? And somehow what we're saying is, can we embed WMP in an LQ space? And the answer to this is given in the embeddings. So you see why these embeddings are useful, because we can actually bound somehow or actually estimate a derivative or a function based on the derivative on the other space. Finally, what I wanted to say is why it is interesting to deal with these distributions. And even though I said it in the lecture, I would like to emphasize this. We have a situation now with distributions when we can differentiate any function. The derivative may not necessarily be a function, but we can differentiate and have everything in a new space called distributions. And this is very useful if you think about it, because when you start with an LP space, you have no guarantee that the functions will be differentiable. But you still want to be able to deal with the derivatives to talk about partial differential equations. So this is why it's so useful to deal with these distributions. Very, very powerful tool. This is the end of these office hours.